Dear students, let us continue our discussion on air refrigeration and air conditioning. Now we are going to start a new module, especially module 5, which is dedicated to air conditioning. Okay, so as the name suggests, it is the conditioning of air. Okay, so and air conditioning, when we think about air conditioning, it is a very beautiful part of our refrigeration and air conditioning subject, or it can be considered as a separate science in itself. Okay, so in air conditioning we are not learning anything new. We are dealing with our the most common things that we experience in our day-to-day life, that is air and moisture, or specifically air and water vapor. So air conditioning is nothing but a simple study of the various properties of various combinations of dry air and water vapor. So before we move on to our more and more concepts of air conditioning, now let us try to understand the basic terms in air conditioning. So first of all, what is meant by dry air? Dry air means it is simply that component of air which is not containing water vapor. Okay, so theoretically it will be consisting of 78% of nitrogen, 21% of oxygen, and 1% of other gases like carbon dioxide, hydrogen, then some inert gases like that. Okay, then what is meant by moist air or moisture? Air containing water vapor. So that portion of atmospheric air containing water vapor in it, that you will be calling it as moisture or moist air. So actually when we are dealing with a totality of the atmospheric air or atmospheric air in total, it means it will be a mixture of, or it will be a mix of dry air and moist air. Then some other terms, mainly commonly dealing with this air conditioning science, we will be dealing with the specific humidity or humidity ratio. Okay, so it is represented by Greek letter omega. Okay, humidity or humidity ratio. So in our common layman's discussions, this term usually comes up. That is, today it was a very humidity or humid climate, so we are sweating profusely. Okay, so what is the idea of this humidity? Humidity means what is the it shows, or it represents the amount of water vapor content in air. So okay, so how we can define this scientifically, or in engineering terms, how we can define this humidity? We can define it as specific humidity or humidity ratio. That is nothing but what is the mass of water vapor present in unit mass of dry air. Okay, so the unit of specific humidity or humidity ratio will be gram per kilogram. So what is the idea of this gram per kilogram? That is how much, or what is the total grams of water vapor, or how much grams of water vapor is present in 1 kilogram of dry air. So if you are taking 1 kilogram of dry air from one portion of atmosphere, what is the total number of grams of water vapor associated with that kilogram of dry air? That is what we are calling it as specific humidity or humidity ratio. Okay, so how this humidity is associated with the well-being or comfort feeling of a human being? So we all know the water vapor will be escaping from the skin surface of all the human beings at all the time, or during 24 hours. We all that will be happening from that will be this evaporation of water vapor, that is sweat will be produced by the skin surface of the human beings round the clock, 24 hours. But knowingly or unknowingly, it is happening 24 hours. And if the atmospheric air surrounding us, the human beings, if that surrounding air is completely filled or saturated with water vapor, then that atmospheric air can no longer take up any more water vapor into it. So whatever sweat is produced on our skin surface, it will be remaining or it will be condensing back. Okay, and we will be experiencing that phenomenon as sweating. Okay, so that is why our elders or our parents usually say, oh, today it is a very humid climate, that is why we are sweating profusely, or we are getting irritated by this sweating. So this you also might be having similar experience. So that is how this air conditioning it is having a very direct impact on our day-to-day life. Okay, so the air in which we live, or the space in which we live, have to be properly conditioned or to be properly optimized so that we can live comfortably in that space. So that is why this term is we are dealing with this term. This is a very important term, specific humidity or humidity ratio. Then another term that comes up commonly in our discussion of air conditioning is degree of saturation, or it is represented by the Greek letter mu. As the name suggests, how much saturated the air is. Okay, so how we can define this in scientific terms? The ratio of the mass of water vapor associated with unit mass of dry air. Okay, so it is dealing with the amount of water vapor associated with the unit mass of dry air. This value divided by the mass of water vapor associated with the same unit mass of dry air, but if it is saturated at the same temperature. Okay, so here we are suppose we are taking some quantity of or some section of this atmospheric air. So we are conducting experiments and finding out what is the amount of water vapor associated with the unit mass of dry air in that air that we are studying. Okay, suppose that air was saturated at the same temperature, then what would have been the maximum amount of water vapor it can hold? Okay, so this maximum amount of water vapor, we will be dividing it we are randomly taking the mass of water vapor at any instant, divided by the maximum amount of water vapor that can be associated with the same dry air. Okay, so now we can consider it as a ratio of these humidity ratios. Okay, or mu can be written as omega by omega s, where omega is nothing but the humidity or the mass of water vapor associated with any unit mass of dry air at any instant. Okay, and divided by omega s. Omega s means S stands for saturated condition. Okay, divided by omega s means omega s stands for the mass of water vapor associated with this unit mass of dry air, but if it is saturated at the same temperature. So degree of saturation is an important term. Okay, then another commonly encountered parameter in our air conditioning is called relative humidity, or it will be represented as a Greek letter phi. Okay, this is also we commonly come across this value. How we can define this relative humidity? So here this humidity is represented relative or in relation to some benchmark or some reference. So what is that reference? How we can define this relative humidity? So it is the ratio of actual mass of water vapor in a given volume of air. So please read carefully. This is the ratio of actual mass of water vapor, where not in unit mass of dry air, but in given volume of air or given volume of dry air to the mass of water vapor if that volume of air was fully saturated at the same temperature. So here when we were discussing about this specific humidity, we have defined the humidity this specific humidity terms per unit mass of dry air. That is, what was the amount of water vapor associated with the unit mass of dry air? That is how we will be representing specific humidity. But when we came to this relative humidity is the mass of water vapor associated with the unit volume of air. So always you understand the difference between this relative humidity and specific humidity. Relative humidity is defined with respect to unit volume of dry air, but at the same time specific humidity is defined with respect to unit mass of dry air. Okay. Then another commonly found term associated with AC or air conditioning is dry bulb temperature. Dry bulb temperature we have been studying from our junior school classes itself. What was that? It is simply the temperature of the atmosphere measured by our ordinary thermometer. It can be a mercury thermometer or any other ordinary thermometer. Okay, so dry bulb temperature is the temperature indicated by the ordinary thermometer, or it is simply the temperature of the ambient air or the atmospheric air. Then another term is wet bulb temperature or WBT. The dry bulb temperature is represented as DBT, dry bulb temperature, but wet bulb temperature is represented as WBT. It is the temperature measured by the thermometer when its bulb is covered using a wet cloth and when it is exposed to a current of moving air. So suppose we are taking the same ordinary thermometer and cover its bulb or this mercury bulb using a wet cloth. Okay, we are wetting a piece of cloth and we are covering the bulb of that ordinary thermometer by using that wet cloth, and suppose we are rotating that this arrangement of this, or this peculiar arrangement of this ordinary thermometer in we are circulating that, or we are rotating that this arrangement in a current of air, or suppose we are rotating that thermometer in ambient air. It is just like exposing that bulb of thermometer to a current of moving air. What will happen? That wet cloth which is covering the bulb of that ordinary thermometer, the moisture in that wet cloth will try to evaporate. Okay, but where does it takes that energy for evaporation? It will be taking the energy for evaporation from the bulb of that thermometer. What will happen? The temperature indicated by that thermometer will be dipping, or it will be reduced, mainly because this wet cloth is taking up heat or energy for the evaporation of that moisture content. Okay, so normally in this ambient condition, the wet bulb temperature will be somewhat lesser than this dry bulb temperature. Okay, so another term here comes up, wet bulb depression. Okay, it is the difference between WBT and DBT, wet bulb temperature and dry bulb temperature. Suppose the difference is, suppose this wet bulb depression is 0. What does that mean? The air, that atmospheric air is completely saturated with water vapor. So the water vapor, the moisture content of that wet cloth is not able to evaporate. So the temperature indicated by the wet bulb temperature or wet bulb thermometer will be the same as the dry bulb temperature. So if this wet bulb depression is 0, it is indicating that this air is that particular atmospheric air can be fully saturated. So this wet bulb temperature and if we know the wet bulb temperature and dry bulb temperature, just take the difference between the two. If it is coming to 0, we can understand that that particular atmospheric air is completely saturated with the maximum amount of water vapor it can hold. So let us continue later.